All right, welcome back. So today we are going to look at infinite series, specifically at the integral test for infinite series. So to look at sort of what we've done so far when it comes to series, we've seen only so many examples. We saw the classic example of the harmonic series. This is a series whose terms go to zero, but whose sum is infinite. An important example, perhaps the most important example, to have mentally in tow. We also saw geometric series, a result related to them, which is to say that if you have a series where each subsequent term in the series results from multiplication by some constant ratio, should that constant ratio be less than 1 in absolute value, we converge to a over 1 minus r, and we diverge when the common ratio is bigger than or equal to 1 in absolute value. This is great, what we've done so far, but that only does so much. What if we want to know about the series sum 1 over n squared instead of sum 1 over n? Does that converge? Does that diverge? What about sum 1 over square root n? Does that converge or diverge? What if we had something like sum n equals 2 to infinity of 1 over n ln n? Now we've got something that's a real funky looking expression. To sort of hint to possible connections here, let me just show a result from improper integration. So this is thinking in terms of integrals. Thinking about the function 1 over x dx on the interval from 1 to infinity, we could apply a limit, replacing infinity with some letter, and then integrate, apply the fundamental theorem. And in fact here, ln b, as b goes to infinity, and we get that the integral from 1 to infinity of 1 over x dx diverges. Now, to see the connection here, note we've got that this integral diverges, and the corresponding sum over here that looks very similar in structure also diverges. Is that coincidental? The question that really is going to underlie what we're going to talk about today is, can results from type 1 improper integrals provide any insight to series? Because if they could, take these three examples that we've expressed here, conceivably, sum 1 over n squared is very much like integral from 1 to infinity of 1 over x squared dx. They look very analogous. 1 over square root n is like 1 over square root x. And this one here with the 1 over n ln n is a lot like 1 over x ln x. So it's like, hey, these improper integrals would all be computable, and could there be any insight that's gleaned? So let's dive into whether or not there can be insight gleaned and what that insight is. Give me a second to scrub the slate and we'll dive right in. Okay, so here's the setting for the integral test. We're going to be looking at a particular series. So essentially we're just adding up a1 plus a2 plus a3 and so on. And what we're going to do, in somewhat bizarre fashion I suppose, but what's going to get integration into the game, is we're going to take the expression for a sub n and replace n with x and let that be some function of x. Now, we are going to demand three things of that function. One, we are going to demand that function be continuous. That's to say that if you graph that function, you would not pick up your pencil to graph it. Two, we're going to demand that function is decreasing, which is to say if you were graphing that function, it would be going downhill throughout its entire graph. And three, we're going to demand that that function is positive, which is to say that function lives above the horizontal axis. So here is a general picture of what these three assumptions look like. Continuous, no holes, jumps, or asymptotes. Decreasing, downhill. Positive, above the horizontal axis. This is the general picture of a function that would abide by the integral test if this function was the expression coming from a series, the terms of a series. So this is the picture that is going to be at the heart of all integral test considerations. Because this picture is at the heart of what we're about to talk about here in just a moment, we're going to need these three criteria to all be in place. We're going to need continuity, we're going to need decreasing, we're going to need positive. But if we get all of these things, we have a beautiful result that follows. So check it out. Assume we've got this series where whenever you replace n with x, you've got a function that's continuous, decreasing, and positive on your interval of interest. So we've got this function that's sort of downhill, don't have to pick up your pencil, and it's above the horizontal axis. And let's assume, this is case one, Assume that the area between that function's graph and the horizontal axis is infinite. Assume that that integral diverges. So I've sort of shaded in the area beneath this function's graph. Assume that area between the graph and the horizontal axis is infinite. Now, I've drawn some bars in here suggestively because these bars actually relate to the series of interest. Check it out. How tall is this first bar? Well, this first bar was at the height of the function at 1, but the height of the function at 1 is just f of 1 or a sub 1. So this first rectangle here is a sub 1 tall. This second rectangle is as tall as the function is tall at 2. This second rectangle is just a sub 2 tall. The third rectangle, a sub 3 tall, and so on. And check it out. Each of these rectangles are exactly 1 unit wide because between 1 and 2 is 1 unit, between 2 and 3 is 1 unit, and so on. So check it out. The sum of the areas of the rectangles would be what? Well, that first rectangle has an area of a sub 1. A sub 1 times 1. The next rectangle has an area of a sub 2. The next rectangle has an area of a sub 3, and so on. But that area, the sum of the areas of those rectangles, is more than the area that's under the function's graph. Because our function is decreasing, because we chose left endpoints here, drawing each of these rectangles protrude beyond the height of the function. And so the sum of a1, a2, a3, and so on is going to be bigger than the integral from 1 to infinity of f of x dx. And that's interesting because the integral from 1 to infinity of f of x dx was infinite, which means the sum a1 plus a2 plus a3 is also infinite. Bigger than boundlessly large is boundlessly large itself. And check it out now. Look what we're doing though. We're adding up all the terms of our infinite series. And so what we have as a result in this case is that the sum n equals 1 to infinity of a sub 1 diverges in this case. So we get divergence of our series when the integral associated with our positive decreasing continuous function was divergent. Hey, that's nice. That's a correspondence. What about in the convergent case? What if we assume, I tried to draw this graph sort of closer to the horizontal axis. What if we assume here, in this case, the area between this function's graph and the horizontal axis was finite? So maybe the area beneath this function's graph and the horizontal axis was, 4 or 25 or whatever real number it is. It's not infinite though in this case. Now, in this case, we're going to use right endpoints to draw our rectangles, making sure that our rectangles stay under the function's graph. Now, how big are each of these rectangles? Well, this first rectangle has a height of just a sub 2 because, the function value at 2 was determining the height there. Here, the function value at 3, this second rectangle has a height of a sub 3. And each of these rectangles has a width of 1. Well, if the first rectangle has an area of a sub 2, and the second rectangle has an area of a sub 3, the third rectangle has an area of a sub 4, specifically, it has a height of a sub 4, because a sub 4, the right endpoint is determining the height, and the width is 1, right? So piece it all together. What's the sum of the areas of the rectangles in this case? Well, we're getting a sub 2 plus a sub 3 plus a sub 4, and so on. And that sum, these rectangles are taking up less area than the area under the function. So this is going to be less than the area under the function's graph. But the area under the function's graph converged here. So the area under the function's graph was some real number. So let's say here, some real number, which means this side here, the area under the function's graph is some real number. And hey, the sum of a2 plus a3 plus a4 is less than some real number. And in fact, it's got to be greater than 0 because our function was positive. And so, hey, this sum has to evaluate to some real number less than whatever the area under the function's graph is. But that means that a2 plus a3 plus a4 converges. And the fact that a2 plus a3 plus a4 converges is going to imply that a1 plus a2 plus a3 converges. Because if you threw in an a1 here, you're just throwing in one number to a sum of numbers that's some real number. Throw in an additional real number to the mix, you get convergent behavior there too. And so looking at these two results, we get convergence of our series when the improper integral associated with our series converges. We get a divergent series when the improper integral associated with our function diverges. We had to assume that the function which resulted was continuous, decreasing, and positive, but assuming that, we get exactly the behavior that we would hope for. So let me pause, clear the slate, touch base on this, and then we can really nail down the idea. So to summarize what we had worked together previously in those two cases that we had, if we consider a series and the expression for that series when you replace n with x is a function that is continuous, decreasing, and positive on our interval of interest 1, infinity, then the series will diverge precisely when the type 1 improper integral associated with our function diverges, and the series will converge when the type 1 improper integral associated with our function converges. Remember, when you've got continuous, decreasing, and positive, you've essentially got this picture working for you. You've got a function that's downhill, no holes, jumps, asymptotes, living above the horizontal axis. So here are three examples. In fact, the three examples that we started off this video with. 1 over n squared, 1 over square root n, and 1 over n ln n. Now 1 over square root n, or excuse me, 1 over n squared, if you write that as f of x equals 1 over x squared, you can see that that's only discontinuous at x equals 0, and x equals 0 is not in consideration. You can see that that's decreasing because as x gets bigger, the denominator gets bigger, and so the function values will decrease. And positive, hey, if x is between 1 and infinity, x squared is definitely positive. 1 divided by a positive thing is a positive thing. So we check all the boxes in terms of the hypotheses for the integral test. We've got to verify that this is true, but once we get this to be true, hey, look at the type 1 improper integral. The antiderivative of 1 over x squared is minus 1 over x, and whenever you plug in b and plug in 1 using the fundamental theorem and subtract, you get minus 1 over b plus 1 over 1, but as b goes to infinity, minus 1 over b goes to 0, and so this improper integral converges, which means since the improper integral, the type 1 improper integral converges in this case, the corresponding series must converge as well. So this series converges by the integral test. Not bad, right? We didn't even have to necessarily assess the sum of the terms in the series because by assessing the associated integral, we were able to get insight to the assessment of the sum of the terms. What about 1 over square root n? Well, hey, as a function, that's 1 over square root x, and 1 over square root x is continuous, decreasing, and positive on our interval of interest, 1 to infinity. Continuous, because x equals 0 and anything less is where you lack continuity. Decreasing, because as you increase x, you increase the square root of x. Increase in the denominator decreases the value of the function. And positive, because hey, square root x is always positive. 1 divided by a positive thing is positive. Life is good here. We satisfy all three criteria of the integral test. You got to check this. But once you do, you got the integral test working for you. You could just consider the type 1 improper integral, which we did do here. 1 over square root x is like 1 over x to the 1/2 or x to the minus 1/2. When you integrate x to the minus 1/2, you get x to the positive 1/2 divided by a half, or rather 2 square root x. So 2 square root b minus 2 square root 1. Here b goes to infinity. Well, that means that 2 square root b goes to infinity. And well, here the improper integral associated with this series diverges, which means if the type 1 improper integral associated with our series diverges, the series to begin with must diverge. So this series diverges by the integral test. Not bad, right? And even something as complicated as 1 over n ln n, while u substitution would be required to integrate this thing, please note 1 over x ln x abides by the three stipulations of the integral test. Continuous, because if we're looking between 2 and infinity, Well, yes, ln n evaluates to 0 when n is 1, well, ln n makes no sense. When n is less than 1, or less than 0, excuse me, we're not worried about all that because we're worried about when, excuse me, n is 2 and greater. And so when n is 2 and greater, we have continuity. We also have decreasing because x and ln x both increase as x increases, which means the denominator is increasing and the function is decreasing. We also get positivity because ln 2 and greater is positive, and well, x equals 2 and greater is positive, and 1 divided by a positive thing is a positive thing. Since we check all the boxes regarding the integral test hypotheses, we could simply look at the improper integral associated with this function. And while yes, you would need to use the substitution u equals ln x to go through the integration, when you use u equals ln x, you'll just get 1 over u, which integrates to be ln absolute u, which in this case would be ln absolute ln x. It's a lot of ln's to consider, but so be it, whatever. Ln b, as b goes to infinity, well, as b goes to infinity, ln goes to infinity, which means what's inside the ln is going to infinity, which means this ln evaluates infinitely, which means the improper integral associated with this series diverges. Since the type 1 improper integral diverges, so too does the original series. We get diverges by the integral test. So what you can see through these examples is that when you have a series whose terms replacing n with x are continuous, decreasing, and positive, man, maybe it's just better to consider, at least something to at least put into our consideration, the thought of considering a type 1 improper integral. That could make life better. If you think about observations that we made about type 1 improper integrals, that would come to our service in this section as well. So I'll cut this video off at this point. I'm sure you'll dive more into this kind of thing when you get into class, but at least, hey, we've got our feet wet with the idea that integration can actually work to the service of evaluating convergence and divergence of series, particularly whenever the expression for your series, replacing n with x, is continuous, decreasing, and positive. When you got this picture working for you, hey, life is good. And, well, that's that.